Alright, so part 2 of my, tutorial series on how to inject code into an ELF binary. We had left off with, we found out how to find the entry point in an ELF binary and how to, change it to whatever we wanted. And where I had left you was we had to find a spot in our binary that we could use to write our own code to. So right now this address obviously is meaningless. We've got to actually find an address in the binary that's going to, be suitable for us to add code to. Now, the definition of suitable is essentially a bunch of zeros. Some people call it a code cave. And I showed you this XXD program. Let me just compile our test program. And we had looked for, code caves manually, and we had found there's one here, small one, and there was a big one up here, right here. But I wrote some code to automate that real quick. So I'm not going to explain this line by line. All it does is it will read in a binary file, byte by byte, looking for, free space that we can write our code to. And what it does is it keeps track of the size and the address where this can be found. And what it does is it'll loop through the whole file, and at the end it'll return the largest space that it finds for us to write code to. So I'll show you this real quick. So all it is again, we're opening our file that we want to search. All this is a structure that I wrote that contains the start address, the end address, and the size of the code cave. Calling it code cave seems to be kind of acceptable terminology that other people have used for this, for a bunch of zeros in a binary file. We call the function, and it will fill in the code cave structure, and it will return the start, end, and size of the code cave. Let's see it in action. Oops. So it finds a code cave. Well, it finds all of them actually, but it's only returned the largest one, 1867 bytes, so it's actually pretty big. Located address 6BE, and we can verify that. We can look up here. We know it's this one. 6B0 is this byte. 6BE would be right over here. So it's accurate. It finds it. 1867 bytes we have to work with. Now, if you remember what our entry point was, our entry point was 400, 400. We can't just change that. Like if we do something like this, uh, 6BE. So let's write that as our entry point. Okay. So the new entry point is 6BE. But that, as you can tell, it's not in any of these addresses. But that's because this is a file offset. 6BE is a file offset. If you look at all these addresses, they're all 400,000 plus 600,000. If I was to break on that, it'll never hit this breakpoint because it doesn't exist. It even tells you, cannot insert breakpoint, cannot access memory address 6B. Now the reason for this is, like I say, it's a file offset. We've got to actually convert that file offset into a virtual address. So what a virtual address is all that is it's the file address translated into a memory address. So when your program is loaded, that 6BE becomes a different address. Now it's pretty easy to convert that on the ELF files. All we're going to do is add something called the image base address to that file offset. Now if we look at the ELF man page again. There's actually something called a program header. So here's a program header. So much like the ELF header, it's got its own structure, and it has a virtual address in the structure. Now, if we use read alpha again, here's the program headers. Now, to find the image base, as far as I know, and again, I could be wrong, you know, I'm a novice as well. I'm just trying to learn as you guys learn. But the image base address is always the virtual address, the first load segment, the first load program header, or the first program header with type load. So here's the type of the program headers: P header, interpreter, load, dynamic. We want the very first header that has the load type. You see there's multiple. It's always the first one. And that virtual address is 4000. So that makes sense, because that would make our offset 4006BE. And if we change our code to do that, so we had the image base, that was the old entry point. We put the new one in, so let's check it out. So now you see, look, that makes more sense. It's within this address space. And if we put a breakpoint on it and run it, now it actually breaks. It breaks out that entry point. And if we look at the bytes, it's all zeros. So we know we're actually in that code cave. So I mean, you know, we're pretty much home free. Now all we've got to do is, you know, put some code there. One thing I want to show you real quick though is the section headers in an ELF file. So these are all the section headers. There can be less, there can be more. And what we want to do is we want to find out in what section header our code cave is found in. The code cave is actually 6BE, so you can actually see it's in section 17, because section 17 runs from 5D8 to E08, and we were at 6B, whatever it was. So it actually runs right to the first byte in the next section. Now, what's important to note about the section headers is the flags. X means executable. And you'll notice that on that section, that bit is not set. Now, I don't know if we actually have to set it executable or not. I don't think we do. But it's a good exercise to actually set executable. I'll show you how to do that, just in case it won't run unless the execute bit is set. But I believe it does still run. And I can't explain it again. I'm still learning as well. But let's see that. Let me show you some of the code I wrote. First of all, to get the image base, you know, again, you can get it through that read elf utility, but if you want to do it programmatically, all you're going to do is read in the elf header, and then inside the elf header it has the number of program headers, so we store that. Once again, inside the elf header is the program header offset, so we're going to seek to that. We're going to read in the very first program header, and we're going to keep reading in each program header until we've read all of them in, or until we find a program header that has the p type of 1, which is actually 1 is the load type, which is what we're looking for. And as I explained earlier, the very first load segment or load program header will have your image base stored in the virtual address. So what we do is we loop through them all, we find a program header with p type equals to 1, and our image base is going to be the virtual address of that program header. So then we return that. It'll break out of that loop and return that virtual address. So pretty simple to find the image base programmatically. But again, if you don't want to do that, you can actually just use readelf to find it. Now we're going to also show you how to make a section executable. What I did was write a function that you pass the file descriptor and the section that you want to change the flags for, or the section that you want to make executable. This actually is, oops, 4. Now, so same thing. What I'm doing here is just basically setting the file pointer to the very beginning of the program, reading in the alpha header. Pretty much the same thing. We're going to grab the section offset this time, and we're going to add to that the section number times section sizes, because we want to basically bypass all the other sections up to section 17. So we're going to go like, whatever the section sizes are, say 50 bytes times 17. That'll place our file pointer right at the beginning of the section we want to read. Then we're going to read the section in, and we're going to do what's called a bitwise OR. What that does is basically our flags, as an example, let's say our flags currently are 0. If we then OR that, a bitwise OR, which should be this, with 4. 4 in binary is actually like this, and that will actually just come out to, it sets all the same. It'll set whatever flags are set in each argument will be set in the result. So it'll equal to 0. It'll equal to 4. But as an example, if our flag already had a 1 in it, so which I think is right. So if our flag was like this in binary, and then we ORed that with 4, then our flag would end up like this, 1100, which is actually 5 decimal. So again, in this case, all we want to do is make sure that that second bit is set, which is actually 4 decimal. So if we do a bitwise OR with the number 4, I can use 4 decimal as well. It doesn't really matter. I just like hex. It will actually set that bit, and again, that bit, the second bit, or sorry, not the second bit, the third bit, will then be set, and again, that bit is the executable bit. And then all we do is we seek back to the beginning of that section and write it out. Oops. Hopefully I didn't mess anything up here. Now let's check my main program. It's going to kind of pull this all together. Actually, no, before that, we've got to find out how to actually write instructions. I want to show you how to, because, whenever we write to that file, when we write to 0x4006BE, we've got to actually write, byte by byte an actual assembly instruction. So how do you get the bytes of an assembly instruction? Because you can't just do a write, jump, whatever. You got to actually write the bytes out. Now, the way that I do it, I'm sure there's a better way than this, but I just use inline assembly in GCC. So all this does is it's going to move our original entry point. If you remember, it was 400, 400 into the register RAX, and then jump into that original entry point. So I put the assembly here, inline assembly in GCC, and then I'll compile it, and then debug it, disassemble main, and you'll see our instructions here, the move and the jump. It's got some prologue and epilogue functions, but all we're concerned about is our 2 instructions, which is the move and the jump. So we'll do something like examine. You can see here the move is actually 7 bytes long, from 4 to 11. So examine 7bx 0x4004AA, and that gives us the bytes. Let me show you. I've already got it set up here for us. So you can see the move instruction, byte by byte. So it's just basically just a character array of bytes. 48 C7. Did I have that wrong? 00044000. So I got a different one. Did I compile that right? .4004AA. So that's a little different. I don't know why I have different bytes in here, but let's change that. Oh no, that's right. I'm not seeing things properly. C0 00440. Okay, so yeah. So you can see, basically I already have it set up. And then if we disassemble the jump is 2 bytes. Plus 11 and plus 13, it's a 2 byte instruction. So, same thing. And it's FFE0, and there it is. So now, let's maximize this. Let's close out of this actually. So now I'm going to take you through the actual main program and what it does. So first we open the file with read and write permissions. We find our code cave, which we know is going to be 6BE. We make the section executable. Again, we already know it's section 17. And then we process the sections. This is for something later on, so you can ignore that. What this does is basically write our new instruction pointer, or sorry, our new entry point. So it's going to be the image base plus the start of our code cave. So it's going to end up being, what we had figured out, which was something like this, 406 BE. And then what we do is we will seek to the exact location on our file, which will be 6BE of our code cave. So again, this is a file offset, 6BE. Then we're going to write our two instructions. So we're going to write the move instruction, which is 7 bytes, and the jump instruction, which is 2 bytes. So let's see it in action. I'm going to recompile the test program. Let me just make sure that nothing changed. It shouldn't change. It should still have our same entry point. It could change though. 400, 400. Okay. So then let me compile the main program. And I messed something up. I see it. Okay. I don't know why I did that. Alright. So now I'll run it against our binary. So there's a bunch of stuff here you're not going to recognize. But basically it says finds our code here at 6BE, 1800 bytes. It finds what section it's in, section 17. And then what it does is it will change the flags. Let's see that it worked. So you can actually see our flags are now, instead of just A, it's AX, so it's executable now. Whereas before it was just A, or it was W. Oh yeah, it was just A. Now it's AX. Then it also finds the image base, and it finds the code cave, which is actually our new entry point. Let's test see if that worked. And it did. And if we run the program now, let's put a breakpoint on it. Whoops. And then run it. So now it actually breaks into it. And if we examine it, the instruction pointer, we can see our code's actually there. So it's moving the original entry point into RAX and then going to jump to it. So if we continue, it executes the code like it normally would. So we've actually redirected output of the or control of the program to our own code, execute our code, and jump back into the original entry point, which then executes the code as it normally would. So it doesn't do anything useful right now, but in the next tutorial what I'm going to do is show you how to actually implement something useful, like a backdoor or some code to actually load your program after it's been encrypted or something like that. Thanks again. Have a good day.